Hello, welcome back. Today we're going to look at Bernoulli numbers. The typical equation when you deal with Bernoulli numbers is the following. It may look very complicated, but today we're going to see what a Bernoulli number is, where does it come from. To understand this, we're going to need a good understanding of the fundamental theorem of calculus. We're going to need to know sigma notations, integrals, exhaustion method when I mean that through areas, and of course the binomial theorem. So, to begin this, let's actually answer where do they come from? Well, Bernoulli numbers arise from the initial pursuit of finding a general formula. Now, for what? Now, mathematicians have always been intrigued and fascinated by formulas that can predict the summations of, for example, any number to the first power and any number to the second power, as here, and I've listed their corresponding formulas. And all of these formulas have been proven. For the cube, so on and so forth. But a question more important than that is, how about for the general p power, for any power? Is there any formula that can predict this? And that's where the Bernoulli number comes from. Now, the way that Bernoulli did over 300 years ago, his way to come up with Bernoulli numbers, I don't even know what he did or how he did it, but I know that he played around with numbers, and that's what I'm going to do, and I'm going to get the same result. Okay, so for my demonstration, we're going to need to understand, we're going to have to go back to area. Now, remember, area was first introduced with the understanding that has a limit definition, and then this limit definition was, with the fundamental theorem of calculus, reintroduced with the integral. Now, we're going to pay close attention to this specific example, the parabola x squared from interval 0 to 3. We're going to look at the area under the curve via exhaustion method. Okay, so here I wrote down the way you would typically use exhaustion method with an infinite amount of rectangles. And here's typical notation, function, here's the width, height, and I wrote this corresponding integral. Now, the point of this is that we're going to try to integrate both sides and then see if there's a pattern we can actually notice. Well, if we take the integral of x squared, we know it's easily x cubed over 3. From interval 0 to 3, just plugging in the 3 will give us 27 over 3, which is 9. Alright, so now we know that, as we saw before, this limit definition of the integral is the same thing as this integral. So these are equal to each other, specifically for this curve. Now, if that's true, we're going to make 9, which is the area, actual area, equal to the limit definition. The limit as n approaches infinity. Now, what I did here, as we saw before, we had a width right here, 3n. But using simple sigma properties, we know that we can extract the constant. So I'm just explaining what I did here. I extracted 3n, and we still have sigma I equals 1 to n, and now I evaluated what the width was, 3i over n, of course, squared. That just leaves us with 9 times I squared divided by n squared. Now everything other than the I can be extracted outside the sigma, which leaves us with limit n approaches infinity. This is 27 over n cubed, sigma I equals 1 n to the n of I squared. Now, if you've done these type of problems, which I'm sure you have, you actually know the formula. You should know the formula. But let's actually go along and solve this. Let's see what we can extract. So here I put the formula for you. I simplified it, and what we're going to do, we're actually going to multiply times this 27 over n cubed and apply the limit. This is where it gets really interesting. So we're right here. I distributed the 27 over n cubed to all of these factors. Then we're going to apply the limit. Now, here we can easily see that the n cancels out. So I can write 9 plus, here there's no corresponding n for it to cancel out. Now the very important thing, that this is super important, is that because there's an n in the bottom, and it's going to approach infinity. Now if we have a huge denominator, this is going to approach 0. Same thing here, it grows 0 even faster. This is 0. So we're left with 9 equals 9. Alright, so we knew that. Now, let's actually reverse engineer it. Now, when I mean reverse engineer, we're actually going to come up with the same thing using opposite methods. Imagine we didn't know what sigma I squared was. So, same problem, 9, limit as n approaches infinity. we were at what, 27, and cubed I'm doing it to the part where we isolated I squared. Imagine you didn't know what I squared was, but you do know that what the limit does, right? Okay, so here we know that limit n approaches infinity 27 n cubed sigma I squared. Now we're going to try to isolate this. Now this 27 right here, it really has no relationship with what the limit is going to do. So in a way we can communicate it with the other side. We can make it communicate. So if you actually simplify this, you're going to divide it to what? That's 9 times 3 n cubed. We can actually take that part out. The 9 will cancel out. Left with 1 equals limit n approaches infinity. What I did, I just simplified n cubed. Alright. We're still left with sigma I squared. Now, what we're going to do here is the following. We don't know what sigma I squared is, but what we do know is that this first term, remember how we said this is the first term, really when you do these type of problems, the first term is the only one that matters, because the other ones are going to have an n in the denominator, which means they'll cancel out as the limit is approached. Well, in here, we're going to actually try to reverse engineer, although we do know what it is, the first term. So, here outside we only see a 1. We don't see an n cubed in the bottom. In other words, this inside, the first term has to have an n cubed on the top. Because when you multiply it times this, it's going to have to cancel out. Now, it's also going to have a 3 in the bottom, because, remember, we're reverse engineering it. When you multiply them together, this must cancel out, this must cancel out, in order for the limit to n approaches infinity, for it not to affect it. So, if you actually consider it and believe that this is the first term, and you actually go along and work it out, it'll give you 1 equals 1, which is true. Now, the other terms, we don't know what they are, because when the limit is approached, the denominator is going to make the whole number approach to 0. So that's the main problem here. But what we do know, we reverse engineered it, and we know that sigma I squared, the first term is going to be n cubed over 3. Okay. You might not see the pattern here, but we're going to actually exploit it. Now, let's do the same thing for a general power. In other words, any number k raised to the p power. Before we designated p power as 2, now we're going to do it as p. So we're going to do it like last time. We're going to use fundamental theorem of calculus, integrate kp, where p is a real number, it doesn't really matter. K, p plus 1 divided by p plus 1, okay? Bound 0 to 2. I chose 2 because it's a convenient number, and we will be able to check it. So once plugging that in, you get 2 to the p plus 1 divided by p plus 1, where p is any given power. Now, let's actually do the limit side. We're going to reverse engineer it just like we did the other time. Well, right here we have a limit as n approaches infinity, sigma I equals 1, and here's the function, we plugged it in. Oh, forgot the I. Okay, we're actually going to work it out. That's 2 to the p, I to the p, and n to the p. And of course, times 2 over n. Here we have the sigma. Now, everything other than the I can be extracted out, for it is a constant. So I can write a limit, n approaches infinity. We'll write 2p plus 1, because we have here 2 to the p times 2, which here there's the power of 1, p plus 1, so using power rule. Not power, yeah, I'll call it general exponent rule, I think that's what they're called. Here, n squared times n is just n cubed. Oh, my bad, that's p. That's p plus 1, same reason. And we have sigma I to the p, where we don't know what sigma I to the p is, but we do know that the whole thing is equivalent to 2p plus 1 divided by p plus 1. Let's actually try to find the equivalent of the first term, because it is very useful. So, in attempts to find the first term, we'll use the same pattern here. We see how this term right here, it has no implications of what the limit is going to do. So we can actually make it communicate over the limit. In other words, 2p plus 1 limit, we can make it go outside of the limit. 1 over n p plus 1 sigma I to the p equals 2 to the p plus 1. All I did is I rewrote it, and I extracted the 2p plus 1 out. Now we see here that that can cancel out. We're left with limit n approaches infinity of 1 over n to the p plus 1 sigma I to the p equals 1 over p plus 1. Alright, we're almost done here. Now the idea is, whatever is inside right here, it's going to have a np plus 1 on the numerator, because in the outside we see no n raised to the p plus 1. In other words, it's going to have to cancel out somehow. So the first term is going to have an np plus 1 on the top. Remember, we're reverse engineering it, because we're going to multiply it eventually times the bottom. And right here in our result, we have a p plus 1. So in other words, we must have a p plus 1 in our denominator. Now, if you just don't understand this, let me actually apply the limit. Now, this has other terms, but it doesn't matter, because there's going to be an n in the denominator, and when the limit is approached, it's going to cancel out. So when this happens, you see how the np plus 1 is going to cancel out, and right here it's also going to cancel out. We're going to be left with 1 over p plus 1 equivalent to 1 over p plus 1. Good. But this is the actual important part. We did all of this just to get the general term, np plus 1, p plus 1. Now this is very important, because for whatever power p, we can actually we actually found out what the first term is using fundamental theorem of calculus. Now, at first you might be thinking, oh, we're done, but no. Remember all these other terms that they were ignored because there was an n in the denominator. Well, it's time to take them into account. Okay. Now going back to the actual video, Bernoulli numbers. This is where the connection comes from. So, for example, we derived the following: k to the p plus 1 divided by p plus 1. The pros gives us the first term of any p power, and the cons, it does nothing else. Now it does something more, but other than that, it's limited. Now when I saw this right here, I'm like, oh, okay, it gives us the first term, but the thing we just finished doing right here has an infinite amount of terms. And it's all determined on what the p is. So I thought about the binomial theorem. Now, I wrote k plus alpha. Okay, let me explain what I did. I wrote, okay, alpha is just any number. I just chose alpha because I don't know what it is. Perhaps that's what I'm trying to find out. And I wrote it as a binomial theorem. Now, using binomial theorem, I wrote here, typical, whatever the power is, p plus 1, choose. Here I'm using r. First term, k to the p plus 1 minus r. And here the alpha to the r. And of course divided by p plus 1. Now, this should look very similar to what we started out with in the beginning of the video. M plus 1 and choose right here, but there's a Bernoulli number in there. So in a way, this alpha acts as a Bernoulli number. But there's something wrong. I put a question mark here because, as you're going to see, this part is incorrect. Now, when I was playing around with this, I was thinking, okay, let me actually make this equivalent to functions I already know. For example, the following: sigma I is equivalent to n plus 1 divided by 2. Alright, so I'm like, let's expand this. N squared plus n divided by 2, same thing as n squared divided by 2 plus n divided by 2. Now, if this thing is true, I should be able to plug in p equals 1, and I should get the same thing. So let's actually work with that. Sigma r equals 0. We're going to do p equals 1, so 2 choose r, k to the 2 minus r, and here we're going to have alpha to the r. You're going to see why the alpha to the r is wrong, but the very reason why I got it wrong actually brought me closer to the answer. Now, here let's actually expand this. That's k squared, or remember, k and n are the same thing. That's k squared plus, I'm just expanding it, k. Now here is 2 choose r, and here r was 0, here r is 1, so that's 2k. We're going to multiply times alpha, because r is now 1, plus k disappears, left with alpha. And my incorrect assumption is, oh, okay, alpha is gonna have to go second to the squared power because it's a binomial theorem. But this is actually an incorrect assumption. Of course, divided by 2. Now this was incorrect because, okay, I tried to find out what this alpha was. For example, I try to compare these equations where k and n are basically the same thing. So I'm like, okay, k squared over 2, okay, that looks the same, okay, no alpha there, plus 2k alpha divided by 2, and I'm left with the k alpha, and here I'm actually left with the n over 2. So k being n, I wrote n alpha equals n over 2, perhaps alpha equals half. But then here we see that this is 0, and then this means that alpha squared must be equal to 0. But obviously this is wrong, because if I square this, 1/4 does not equal 0. So the main problem with this assumption is that it's not an actual binomial theorem. It's not this alpha does not it's not determined by the power, but they're actually different numbers. So using more examples, I can actually come up with this. So let's say let's use the same problem. Let's use sigma I, in which we were with n squared over 2 plus n over 2, and then let's use the limit definition. We were expanded at n p plus 1, p equals 1. We have k squared plus, here we have k, we have 2 thanks to the choose function. Here we have alpha, but now I'm not going to consider it as a power. I'm going to consider it as a as a constant. Now these constants are going to be different. They're going to be different. For example, here we have alpha 2. So now here we see how the function is completely characteristic by having n variables. So whatever doesn't have an n variable gets deleted. In other words, this thing right here, the term without a k or any variable, means that it's going to have to be equal to 0. So let's go ahead. Here everything was divided by 2, remember? So we have k squared divided by 2 plus, oh, another thing, I forgot, there's an alpha 0. Remember, if they're going to be coefficients, they must be everywhere. Alpha 1 divided by 2. Let's actually simplify. Here this is going to simplify. We're left with alpha 0 k squared, and this is, remember, with alpha being equal to what Bernoulli number is. You can make this equal over here. K and n are basically the same thing. They cancel out, and that means that pretty much alpha, if we extract the 2, alpha 0 must equal to 1. Okay, this is actually the first Bernoulli number. And you must be thinking, okay, this must be a circular proof because we're using a formula we actually already know just to find Bernoulli numbers. Isn't this counterintuitive? Well, at first it is, but actually we can use a similar idea. First, let's keep on finding the basic Bernoulli numbers. Here, k alpha 1 equals n over 2, where k and n are the same. That means that alpha 1 must equal to half. We found the second the second Bernoulli number. Now, as you've said, this will actually be a circular proof. But let's actually stop there, and let's actually derive it without using any circular proofs whatsoever. So, using this same idea, where this is not a power anymore, but they're different constants, let's actually figure it out. Let's start with basic examples. Okay, let's start with, let's say, we already found the first two Bernoulli numbers. Let's find the third one. So, in other words, alpha 3. What's alpha 3? How are we going to find that? Well, let's actually make p equals 2. Let me find the summation of I squared. Imagine I did not know that. Let's actually just use our formula right here. So we made p equals 2. We're interested in the squares, so we're going to make k squared. Okay, we're just expanding it. Please keep that in mind. There's an alpha 0. We did find alpha 0 and alpha 1. Plus, there's a k right here. Alpha 1. Here, p equals 2, so that's 3 choose 1. That's going to be a 3 here. Plus, here there's, of course, that's actually k 2 3. This is actually 3, my bad. This should be squared. Then we have another k right here. And 3 choose 2 is the same thing as having, let's see, 3 factorial, that's 0, 1, 2. That's 3 minus 1, 3 minus 2 is 1 factorial. Here we have 2 factorial, same thing as 3. So it's 3k alpha 2, and of course we have the alpha 3, which doesn't matter at all because we've shown it before. But imagine we're right here, right? We know what alpha 0 and alpha 1 are, but we don't know what alpha 2 is. So let's actually try to anticipate what the result is. Now, when I say anticipate is the following. Okay, so alpha naught was 1, so we're gonna have k. Of course, the whole thing was divided by p plus 1, so the whole thing is gonna be divided by 3. We're gonna have k cubed over 3 plus. Here we have 3k squared alpha 1 divided by 3, and here we have plus 3k alpha 2 divided by 3, and this is what we're actually trying to find. Now here the 3 cancel, we actually know what alpha 1 is due to the previous exposure that we've had, plus I'm going to leave the 3's like this for a reason. Here there's going to be half, alpha 1 is half. So here we're going to have 3k alpha divided by 3. Now let's actually remember, this will give us the function, the function to predict the summation of certain numbers. In this case, summation of squares. So let's actually think. Whenever we plug in k, for example, k equals 5, that means the first 5 numbers. So if the summation of I squared, imagine we plug in the first number, 1. 1 squared is simply 1. So let's plug in 1. The summation must equal to 1, in which k is 1. So that's 1/3. I'm just plugging k equals 1. Here, the 3 is going to cancel out. Actually, no, I shouldn't. Here there's a 3 everywhere, and this is why I did this. I'm going to make it, I'm going to extract it and multiply it to the other side. 3 equals, here 1 cubed is 1, plus, here that's 3 over 2, k equals 1, and here we have simply 3 alpha. Okay? It should be alpha 2. So here we have k equals 1, alpha, that should be good. Now let's actually isolate alpha 2 like we would with any other variable. That'll cancel out. 2 equals 3 over 2 plus 3 alpha 2. Okay? So then isolate this. 2 minus 3 over 2, that gives you 2, 4 equals what? That gives you 1/2. So 1/2 equals 3 alpha 2. Okay? And simply divide by 3, and we're left with alpha 2 equals 1 over 6. Okay, and you can use the same pattern that we've just done. We can actually think, okay, plug in, let's say, 1 into the summation series, and then plug in 1 to the function, and then you can keep on isolating Bernoulli numbers like this. So we actually found the third Bernoulli number, which is 1 over 6. Let's actually go to the fourth one. One more example, so you can see how I actually came up with this. So we're going to make p equals 3. P equals 3, and remember, using this equation, we're just going to plug it in and expand it. We're going to have k to the 4th. Okay? Now, nothing is done to choose because it'll just be 1. K to the 3rd. Okay, now we're going to have to take into consideration. Here, of course, there's alpha naught, which we do know what it is. Alpha 1. Here, that's 4, choose 1, which is just simply 4. Here, then we're going to have to do k squared, alpha 2, which we know what it is already. And then we're going to have to find this number, which is going to be 4, choose 0, 1, 2. That's just going to be like this. That gives us 4 times 3 divided by 2, 6. Then the next one, plus k, alpha 3. And this should be 4, thinking about it as a mirror. And remember, anything that doesn't have the variable anymore is completely useless. And the whole thing was divided by p plus 1, which in this case would be 4. Okay, this should equal the summation of I to the 3rd. Now let's actually find what it is. Now, we know what alpha naught is, so we're gonna fill in the Bernoulli numbers that we actually know. So the only problem that with this thing is that it's quite slow. For example, if you want to find the sixth Bernoulli number, you're going to have to know the first, second, third, fourth, and fifth. But you can actually still find them. So alpha naught was known as to be 1. 1 times k fourth is k fourth divided by 4. Here alpha 1 was known as half. So half times 4 is 2 plus 2k cubed. Here alpha 2 is known as 1 over 6, which is just k squared. And we don't know what what the fourth Bernoulli number is. So we're going to write fourth k alpha cubed, and we're going to use the same idea. The first term, what's the first? What's the summation of the cube numbers if there's only one term? In other words, 1 cube, which is 1. So 1. We're gonna have to plug in k equals 1 here. So that'll be 1. Wherever we see k, we're just putting in 1 to the fourth is 1. Plus k 1 cubed is 1 plus 2. Here that's just another 1. So that's 1 plus 2 plus 3. That's 4 plus 4k alpha third divided by 4 equals 1. We're going to move the fourth to this side. Okay, we're going to have to subtract minus 4 because remember we're isolating, and we're left with a neat idea. I'm sorry. When you divide the fourth, you're left with 0 equals alpha cubed. Remember k is 1, so we're left with the fourth Bernoulli number is actually 0. Now these numbers are super interesting because what they do, they're actually the coefficients in order to make these summation functions possible. Now these numbers go they don't stop, but so far if you actually note the numbers we've actually done, we found 1 over 2, 1 over 6, and then we've seen that it goes to 0. Wow, these numbers are very, very, very confusing because here they're decreasing, and then we're actually going to see that they increase. So using this technique, you can at least basically see how Bernoulli numbers arise and how they come up. Bernoulli numbers are very useful not only for this, but for other applications, but there are other algorithms that could come up with Bernoulli numbers. Thank you. Subscribe.